This is our investigation of absorbance in fluorescence lab with Isabella, Taya, and Ethan. This is LB 247, section 4 with Dr. Sawtelle. This lab is going to include our background information, representations, experimental design, data graphs, error improvement, discussion, scientific reasoning, and our conclusions. For background information, we used Beer's law, which states that the absorbance of a material sample is directly proportional to its thickness or its path length. We used the known intensities to calculate the absorbance, and this helped us to calculate the concentration of the dye to determine the type of substance that we were measuring. We also wanted to talk about absorbance and fluorescence spectra differences. The light coming through the cuvette in an absorption spectra will show absorbance at a specific wavelength. When light comes through the fluorescent dye in the cuvette, there will be a similar absorption at the same wavelength, but there will also be an emissions value on the graph with longer wavelength. For the first representation, the graph is describing the movement of a photon once it encounters excitation. The single-headed arrows represent jumps that the photon makes when it changes from ground state to the excited state, and the double-headed arrows describe the oscillations that occur. Oscillations seen in the first graph are similar to the oscillation behavior seen in the Lennard-Jones potential graph that represents interactions between two atoms. For our experimental design, we used a spectrophotometer, 2 unknown dye solutions in a cuvette, one we chose, one the other group chose, and water in a cuvette. For our procedure, we set up the spectrophotometer to record spectra of light coming through the cuvette containing the dye solution. We used the known absorbance graph to compare the data we collected with this experimental setup in order to determine the type of solution that we were given. For our data collection, we have a few representations of the raw data that we collected during this phase. The graph on the left was what we first saw. Then we were able to determine the wavelengths and the intensities in order to calculate our absorption using Beer's law. From this, we were then able to create graphical representations of our findings.
Here's the graph of the absorption spectrum of the Lapidus dye. You can see there is a peak of absorption around 566 nanometers for this specific dye. We used this absorption equation in order to calculate the concentration of the Lapidus dye by using the extinction coefficient, which was 43,000, the absorption of the dye, which was about 0.73, and the path length of the light, or the thickness of the cuvette, which was 1 centimeter. Our next graph shows the fluorescence absorption and emission of the fluorescein dye. We observed a peak of absorption and emission for the fluorescein at around 500 nanometers. But as you can see, from 600 to 900 nanometers, we also observed another peak that is likely due to light interference from either the moving flashlight or an outside light source.
We had some error in the graph and experiment that included the light from outside sources affecting absorbance and the interference of the flashlight when measuring using the spectrophotometer for the fluorescence graph caused an unnecessary peak in our graph. So some improvement ideas are to isolate the experiment in a completely dark room with night vision goggles and to use the flashlight that has better ability to create a smaller beam of bright light rather than the wider one, and use prongs to hold the fiber optic cable, cuvette, and flashlight in place. These are the answers to discussion question number 3. So a certain wavelength photon goes in to excite the electron to a higher energy state, and then the resulting molecule goes back to the base state where the simple harmonic oscillation occurs at the excited state, and then it will drop emitting that photon of longer wavelength, and then go back to that ground state simple harmonic oscillation. This means the energy jump from step 2 has more energy than the drop from step 5. Since different wavelengths of photons have different energy levels, the emitted photon will have a different length than the excitation photon. For part B, energy is still conserved even though you have a different excitation and emitted photon because it takes energy to get to the simple harmonic oscillation states. And then for part C, it is very important to have a dark environment and the light source to be 90 degrees from the fiber optic cable, because otherwise you will get light interference in the cable, which means you also see values from the absorbance spectrum of the regular flashlight. In this experiment, our group passed light through an unknown substance and tested its absorbance spectrum. We also tested the absorbance and fluorescence of fluorescent. We know we did not get the correct spectrum for fluorescent because the emitted photon should always have a longer wavelength than the absorbed photon according to the image to the right. Finally, we used Beer's law in order to calculate the unknown's concentration after identifying the unknown as Lapidus, using the idea that the unknown's absorbance spectrum matches the Lapidus that we already know.